This is Thermochemistry, Part 5. This is an advanced part of the molar phase change and specific heat capacity problems. It is assigned to some classes but not to others. So we're looking at combining molar phase change heats and specific heat capacity problems. And here we're looking at a heating curve. This is going to be your degrees Celsius here and joules increasing as we go in this direction. And each one of these line segments represents a different part of the heating curve. So if we're looking at part A, this is where we have completely solids. So here we would be looking at the specific heat capacity of water. This would be a Q equals mc delta T region. Region B, this is where we're staying at the same temperature. We're going from a solid to the liquid phase during this portion of the curve. So in this portion of the curve, we're looking at water's delta H of fusion. So we're in region B. Now I want you to notice that some of these constants I'm giving to you in joules and others I'm giving to you in kilojoules. Let's get everything in the same units. It'll make life a whole lot easier. So 6.0 kilojoules is the same thing as 6,000 joules. The next portion that we're looking at is C. This, we are completely in the liquid phase. This region, we would be using Q equals mc delta T. So we would want the specific heat capacity of water. So this matches up to region C, right there, specific heat capacity of water. Now we're in region D. We're going from the liquid to the gas phase. This is water's heat of vaporization. So this is the D region on the curve. Once again, we want to make sure that we're consistently using the same units. So we're going to use 41,000 joules per mole. And then the last segment, in this area, we are completely in the gas phase. And I have not provided you with the constant for the specific heat capacity for the steam phase. So we're not going to do anything with that. So let's look at this question here. It says how much energy is required to convert water at the solid phase at minus 10 degrees C to water in the liquid phase at 50 degrees C. Let's try highlighting what we've got here on this curve. So we're going to start at minus 10 degrees C. And minus 10 degrees C is going to be about right in here. So we're going to look at this region. All right. Then we've got to heat the water so that the ice is completely converted to the liquid phase. So during this entire time, we're not going to see any temperature change. We're just melting the ice. Once we get the ice completely melted, then we can increase the temperature to 50 degrees Celsius. So we'll go about halfway up the curve. So we can divide this curve into three different portions that we're going to be looking at. There's part 1, part 2, and part 3. And we have to calculate the energy that is required to make each one of these changes. So let's do the first part. So we're going to do part 1. Part 1, we're going to take the solid ice from minus 10 degrees C up to 0 degrees C. So let's go ahead and work this part of the problem. This is going to be a Q equals mc delta T problem because we do see a temperature change. So Q is going to equal, I forgot to tell you how much water this is. Let's say that this is 100 grams of water. All right, I should have specified the mass to start with. So we're going to have 100 grams of water. So Q equals 100, and let's put a decimal point over there just to give us some significant figures to work with. Q equals 100. I'm in the solid phase, so I'm going to use C water of 2.1 joules per gram. So there's my C. And my delta T, I'm going from minus 10 to 0, so I've got a change of 10 degrees. I figure all this all out, and I'm going to put it way over here because we're going to have to line things up. This ends up being 2,100 joules. This is part 1. I'm going to put a circle around this so I remember that I have to do something with it. All right, I've gotten it up so that it's all at 0 degrees C. Now I've got to melt it. So now I'm on step 2. So let's do step 2. Now I'm taking H2O solid to H2O liquid. And the whole time I'm at 0 degrees C. So now I'm going to have to solve this as a conversion factor problem. So I have 100 grams of water. I'm going to end up using the delta H of fusion because this is the fusion region. So I'm going to be using 6,000 kilojoules or 6,000 joules for every 1 mole of water. So first I have to get my water over into moles. So I've got grams of H2O, and I have to convert that to moles of H2O. So this would be 18.02 grams. So now I'm over to moles of H2O, and now I'm going to use my conversion factor here that says that for every 1 mole of H2O, I need 6,000 kilojoules, 6,000 joules. So I'm going to multiply everything on the top, divide through by on the bottom, and I will get 33,296 joules. I'm going to put a circle around this, so remember that I need to do something with it. That is 33,000, so that is a comma. So 33,296 joules. Now, notice here that I have shown 5 significant digits, even though there was only 3 in this. I'm not going to correct for significant digits until I get to the final answer. That's what you should always do. Carry all your digits through until you get to the very end, and at your final answer, correct for significant digits. All right, now I'm on step 3. I've gotten through to this point. Now I need to bring my liquid water temperature up from 0 degrees to 50 degrees. So I'm taking liquid water from 0 degrees to 50 degrees C. So this is a Q equals MC delta T type issue. So we've got Q equals MC delta T. Let's go ahead and solve for that. So Q equals, I still have 100 grams. My C this time, for liquid, I'm going to look up here. For liquid, it is 4.2 joules per gram. And then my delta T is 50. So I'm going to take all of these, multiply it together, and I get 21,000 joules. Okay, I'm going to put a circle around this because I'm going to need it. So what I'm going to do is I'm going to add parts 1, 2, and 3 together. So I'm going to add all of these up. And in my final answer, I'm going to have 56, and I'm going to round here, 56,000 joules. So that is my final answer. Let's put a box around it because that is the very, very final answer.